All right. Well, hey there, everyone. So let's see. Today is day 27. We only have one more lecture to go. So Monday's a holiday. It's Memorial Day. I trust you all to do your patriotic duty and barbecue and so forth. And then we'll have our last topical lecture on Wednesday. We will review on Friday. And then we've got a late final, which is a week from next Friday. So 2 weeks from today is our final. And let's see. Did I have anything else I needed to say? Yeah. So any questions before I get started?
Yeah, when are you gonna upload a grade scope submission for 8.4? Or like when is that?
Oh, yeah. I was going to do that. Thanks for reminding me.
No problem.
Okay. All right. So, let's see. I trust everyone has watched the videos, and there were a few problems in the videos. So let's start with this new term. We've already learned about elementary regions. Now we occasionally talk about symmetric elementary regions. A symmetric elementary region is where any one of x, y, or z can be bounded between between two functions, rather, of the other two variables. So, yes or no, folks, is the cube a symmetric elementary region? Yes or no? Yep. Yeah, cube symmetric. Okay. Yes or no, folks, is the unit ball a symmetric elementary region? Yes or no? This one. Yes, it is. In fact, how about, okay, someone who said yes, Timothy, express the unit ball with y being between two functions of x and z. Y is between some function depending on x and z, and between some other function of x and z. What would those two functions be? Oh, nice. All right, good job, Timothy. Yeah, so if you sliced the orange this way, then the piece on the right, this one, would be where y is positive root 1 minus x squared minus z squared, whereas the other side would be where y is negative root 1 minus x squared minus z squared, and the interior of the orange is between those two functions. Okay, moving on. Yes or no, is this cone z greater than or equal to square root of x squared plus y squared an elementary region? Or sorry, a symmetric elementary region. Yes or no? because it apparently extends indefinitely. Okay, and we're like the interior. So it keeps on going up. We would say this region is unbounded because it extends indefinitely in the vertical direction. Oh, Nikhil is asking about symmetric across every axis. Yeah, so my use of the word symmetric here doesn't actually have anything to do with the way we usually use the word symmetric. It's an unfortunate choice of terminology, which I didn't make, but this is what the book uses. They just mean it's symmetric in that any of the variables could be expressed to lie between functions of the other two, but you can have shapes that don't have any, say, mirror symmetry or rotational symmetry that are still nevertheless symmetric elementary regions, according to this definition. So I say that the cone is not. Could someone tell me why it's not? Remember, symmetric region or elementary regions rather need to have a function on top and a function on the bottom, or a function in front and a function in the back. Ah, nice, Martha. Yeah, so it extends indefinitely. What would be the function on the top? There's no roof to this thing. It's like there's a lower function given by the surface of the cone, sure, but there's no upper function. So it's like z is greater than something, but it's not less than anything. So yeah, no, this is no, it's unbounded. There's no roof to this shape, let's say. Okay, next question. How about the torus? Is the torus a symmetric elementary region? Yes or no, folks? Oh, and Nikhil asked if we constrained it. You mean to lie below 5? But above the cone? Yeah. If you capped it at some point. Then let's see, you could, yeah, it would have a top and a bottom, a left and a right, front and a back. Yeah, in that case, yes, it would. Okay, so let's see. The torus, I think I saw some no's there. The torus is a negatory. Why is that? How about Ziyuan?
Well, I just remember from the lecture that you can make a line across the y-axis and it's like intersect the torus at 4 points.
Oh, okay,
That's my
very good.
reasoning.
Yes, so if let's say this is the y-axis points left to right here. So if I drew a line in that direction, it would intersect in 1 point, and then 2 points, and then 3 points. Let me draw this better. So I'm trying to draw a line that intersects in 4 different points, right here, right there, and right there. Clearly, there can be no way to express this region as having a single function on the left and a single function on the right. Looks like you would need at least 4 functions instead of 2 to describe the inequalities for this region. The cone, oh, Seth's asking about the cone. The cone apparently is not even elementary. Yeah, our definition of elementary, well, it started with the definition of a simple region, which were always bounded, right? Like a simple planar region was constrained to lie between an interval and 1 function on the bottom and 1 function on the top. So that's definitely bounded, because the interval a to b is bounded, and these functions on the bottom and the top are continuous. That's not necessarily obvious, by the way. It's obvious to me because I do analysis like for a living. For you, however, you would have to know a certain fact, which you might have heard about in calculus. Tell me if this sounds familiar. A continuous function on a closed interval attains its minimum and maximum values. Does that sound familiar? A continuous function on a closed interval attains its minimum and maximum values. Absolute extreme degree. Maybe, I'm not sure I know it by that name, but that could very well be it, Dimitri. So yeah, the point is there is a maximum for these functions on the top and on the bottom. So there's no way that this region could be unbounded because, well, this function has a maximum value. Dimitri's asking if it's related to the mean value theory. Is it related to the mean value? I think you can prove, I'd have to double check this. You may be able to prove one of the mean value theorems using that fact. But anyway, so in either case, it follows from our definitions that elementary regions are always bounded. But you can still extend our theorems to unbounded regions. We haven't done that yet, so that gives me an idea. Maybe I should do that. It is possible to generalize our theory to unbounded regions. We just haven't officially done that yet. Okay, so after all this talk about symmetric elementary regions, I give you the divergence theorem first for symmetric elementary regions, but then I almost immediately generalize it to regions that can be chopped into symmetric elementary regions. And you know what, here, I'll get to that in a second, but first, let's try applying our new theorem, our big theorem, which we've been waiting pretty much this entire class to get to, the divergence theorem. And the first thing that I want to do with it is apply it to a problem that appeared on midterm 2. The problem about the flux of light out of an octahedron. So on the right here, you can see the original midterm problem and its solution. At the time, the only tool that we had available to us to answer that question was surface intervals. You had to attack it directly. So what would be an alternate approach now that we have our more powerful toolkit? maybe, how about I let W be the octahedron? And yeah, it does look symmetric, or I should say symmetric elementary, because it's got one pyramid on top, or one pyramid face on top and one pyramid face on the bottom, and similarly with the front and back and the left and the right. So, in fact, let me say this a bit more carefully. Let W be the interior of the octahedron. So that S, the surface of the octahedron, right, these faces, is the boundary of W. Now, the midterm question asked you to compute the flux of the given vector field through the surface. Okay. So what does divergence theorem say we can do instead of doing a surface integral? Okay, so we'll integrate the divergence of F. Good. Okay, so by the divergence theorem, we can make this a triple integral if we take the divergence of that. And now it's over the volume that I call W. So I took a surface integral, turned it into a volume integral. That's what the divergence theorem says you can do. Does anyone know why this might be preferable? I'll do a little computation here. Del dot F, let's see, F, I don't know if you can see it, but it's just X, Y, Z. Okay. So del dot F is partial X of X plus partial Y of Y plus partial Z of Z, which is 1 plus 1 plus 1. Yeah, I think it's easier. So for one, you're integrating a scalar instead of having to like parameterize the surface and compute the normal and take the dot product of the normal with your vector field. Now it's just integrate a scalar over a volume. So I think it's a lot simpler. So what do we get then? It's the triple integral of 3. Could someone tell me what's that equal to? Oh, good, we can pull the 3 out. Yeah, and what happens when you integrate 1? You get the volume. Good. So we get 3 times the volume of the octahedron. So yeah, I think it's easier to solve the problem that way. Finding the volume isn't necessarily obvious. It kind of helps maybe if you know the formula for the volume of a pyramid. I'll find the volume right now. How about the portion in the first octant by using the pyramid volume formula, because this is a region with height 1 and base equals 1/2 of 1 times 1. And the volume of this tetrahedron is so the tetrahedron volume formula, or the pyramid volume formula, I'm just going to use it. You can prove it or derive it. I'm just going to use that it's 1/3 the area of the base times the height. And that's just 1/8 of the entire octahedron. All right, so for our answer, we get 3 times 8/6, which is 4. And hey, the same answer we got previously as well. That's good. Martha was asking if I used the given vertices. I used the given vertices to determine the dimensions of this tetrahedron. I used the given vertices to see that the height of this, which is 1/8 of the whole shape, is 1, and the base is a triangle with legs of 1 and 1. Okay. So if there aren't any more questions on this one, now perhaps you see the power or utility of the divergence theorem. It's great. It's really powerful theorem. I use it all the time in my research. Here's another question. How about you all do this one? Private message me the answer.
Is that sine x plus y squared? Is that just sine x plus y squared?
Yeah.
Okay.
Although, actually, I think it doesn't matter. Oh, okay, yeah, Andrew got it.
Oh yeah, doesn't matter.
Ah, cool. Oh, good. I'm getting some right answers. Okay, so yes, you all that have started taking the divergence saw immediately that the divergence is 0, so the flux is 0. So imagine how long that would have taken if you had tried to do a whole surface interval now. Good, yeah, so it's 0. Okay, so now here's what I was talking about generalizing Gauss's theorem. Generalize it to regions if you can split them up into symmetric elementary regions. I think you could probably generalize it to regions whose boundaries or surfaces that, I probably shouldn't say that. I'm just thinking about generalizing it to infinite regions. But I didn't prepare to talk about that, so let me not go that far into left field. Let's practice with this generalization of Green's theorem to more general regions, because the coconut would be an example of one of these more general types of regions. So in this example, I define B to be the space for which the distance from the origin is between 2 and 3. So it's kind of like if you put the origin at the center of this coconut and you said the inner radius of the coconut is 2 and the outer radius is 3, then B corresponds to the flesh of the coconut, the part that you would want to eat. So it's a volume, it's a solid volume that's outside of one ball but inside of another. Yes or no? B is a symmetric elementary region. Yes or no? Oops. Okay, good. Yeah, it would not be a symmetric elementary region because it has, you drew, say, a vertical line through it, it would intersect in 1, 2, 3, 4 points. But it's possible to chop it up into a bunch of pieces that are. In either case, let's verify the divergence theorem for this shape. What's kind of interesting is orientation. So I said that when we have a closed surface, by convention, we choose the normal to point into space. That is away from the interior of the object. So I think probably most of you would intuit that the normal would point away from the coconut on the outer boundary. Which way should the normal point on the inner boundary? Yeah, it should point away from the flesh of the coconut, which means it actually points inside. So yeah, in the interior of the coconut, right here. Okay, so on the outer boundary, where r is equal to 3, the unit normal is the positive r hat direction. But on the inner boundary, where the radius is 2, the unit normal is the negative r hat direction, because it needs to point away from the coconut flesh. Okay, so using that, let's compute the flux of this vector field through the boundary of the coconut in 2 different ways. So we want to show that flux of F through the boundary is equal to the volume integral of the divergence. So how about I get some folks to calculate one of these and some to calculate the other, and we'll see if we get the same answer. So let's see, let me pick, how about Andrew, Seth, Nikhil, Martha, Patricia, Caitlin? Do this one. Evelyn, Roland, Timothy, Zuyan, Dimitri, Justin, Kevin? Do the other one. We'll see, and private message me when you figure it out, and let's see if we get the same number. And you'll need the formula for F, by the way. It's R hat over R. Kind of interesting. I'll give you a hint for volume and surface integrals in spherical coordinates. In spherical, EV is usually we use rho in spherical, but rho is the same as R, so I'm just going to use R, okay? Yeah, private message me when you get an answer. Let's help out the surface integral folks for a moment. So on or where r is equal to 3, f dot es will equal r hat over r dot. The normal is, we already said, r hat. We actually just get 1 over r ds, which is actually, if r is equal to 3, that 1/3 ds. So just, I guess it'll just be 1/3 of the surface area on the outer integral. And then you can do a similar calculation on the inner one, but let me help out the volume integral. Let's see, I guess we're going to need to compute del dot f. I think right off the bat, it's going to be easier to write it as del dot r over r squared. It's a bit easier. It's like partial x of x over r squared plus partial y of y over r squared plus partial z of z over r squared. R hat is the unit vector in the direction of r. So it's r over the length of r, which is the same as r over r. And r is x, y, z. Why did I multiply? You mean right here, Martha? This week? That is n dot ds. So the vector ds, you may recall, is n hat times the scalar ds. And I just plugged in that was the normal on the outer surface. Okay. Now the coconut has two boundaries, the outer one and the inner one. So we're going to have two integrals, and we're going to add up those two surface integrals. Let me do some more computation here. So this is going to be low E high minus high E low dx of r squared equals 2x. So square the above. Well, anyway, it looks like by sort of symmetry with the first term, the second term will be r squared minus 2y squared over r to the fourth. And then r squared minus 2z squared. What do we get? 3r squared minus 2x squared minus 2y squared minus 2z squared. It's 3r squared minus 2r squared. It's just r squared. So after all that, we just got 1 over r squared being the divergence. Now, what about r equals 2? Back to the surface interval term. In this case, f dot ds is going to be r hat over r dotted with, well, again, it's n, but now n is negative r hat ds. Because this is what I was trying to illustrate when I drew the inward pointing normal on the inner surface. It's pointing towards the origin now. What I was saying right here. So we get just negative 1 over r ds, which is actually negative 1/2 ds, since r is 2. I did get a couple of answers submitted, but they weren't quite right. So far, no one else has submitted an answer. So let's see. I guess we'll go back to the volume integral. The integral of del dot f dv. We're doing it in spherical. What are my spherical bounds? Oh, Dimitri, yeah, that's it. That's what I got. Good. Okay, yeah. So the region corresponding to the coconut has r from 2 to 3, and then theta and phi over their usual range of 0 to pi, 0 to 2. And let's use this. so that's not a hard integral to compute. In fact, the r's even cancel. It's kind of nice. Yeah. So we get that this is 2 pi times integral of sine from 0 to pi is 2, as hopefully you all know by now. Here, I'll just write it. Okay, so we got 4 pi doing the volume integral. Nikhil's asking R magnitude. It's the square root of x squared plus y squared plus c squared. That's how you take the magnitude of a vector. Yeah, so R squared is x squared plus y squared plus c squared. That was a 2, I think that was a 2r squared. Yeah, I factored the 2 out. This plus this plus this is r squared. So for the surface integral part, let's see. F dot ds on the boundary, oh, was it B? The boundary, here's maybe the trickiest part. Okay, no, not tricky, but what's the word I want to look for? The newest conceptual part to this problem right here. The newest concept is what I'm about to show you right now. The integral of the flux of F through the boundary of this coconut consists of the integral of the vector field through the surface. The boundary of the coconut consists of the outer surface and the inner surface. So this is 2 integrals. So this will be the integral of F dot ds over the outer surface, which was where r was equal to 3, plus the integral of F dot ds over the inner surface, which was where r was equal to 2. Okay, that's the main new concept that I wanted to impress upon you with this generalized region to which Green's theorem applies. Or sorry, to which divergence theorem applies. And what's kind of weird is that we effectively subtract this term because the normal points in the opposite direction that it usually points in. So the first surface integral has the usual facing normal. We already calculated that F dot ds is 1/3 ds right there. And on the inner one, where r is equal to 2, we already found that's -1/2 ds. So I'm going to get 1/3 the surface area of a sphere of radius 3 minus 1/2 the surface area of a sphere of radius 2. So what's this? 12 pi minus 8 pi. Hey, it's 4 pi. Same. All right. Yeah, so this problem really packed it all in. everything we've been learning all in one problem, including some new concepts. So yeah, that's why I'm a fan of this problem. That's why I made an announcement about it. I thought this would be a good challenge for everyone and a good long problem and a good satisfying end where you get to see two answers that agree, even though it seems like we came about them via very different methods. So cool. Sorry for going over there, folks. That's it. I'll see you all on Wednesday and have a nice weekend.
Yes.
Hi, Professor. I just wonder, can this theorem be generalized to like any closed surface?
Any
in
what?
Like any closed surface, can we apply this theorem? Because in theory, every closed surface can be broken down into infinite amount of simple symmetric.
When it requires an infinite number, that's when you run into the risk of things not converging. And there's also very rough surfaces, which we haven't talked about in this class, but it's possible to describe surfaces that are like non-differentiable or very jagged or rough. Everything in this class is smooth, or at least piecewise smooth, and there's only a finite number of pieces.
Okay, cool. Thank you.
Mm-hmm. Yeah, sure, Timothy.